A supernova type 1a is an explosion of nearly constant luminosity with peak primarily from decay of nickel and later luminosity primarily from decay of cobalt. And that may be due to an exploding white dwarf that has reached a critical mass, i.e. 1.44 solar masses, via accretion from a secondary and a close binary. Let's take a look at what we know about this supernova type 1a. If we just take a look at an exploding event and we take a look at luminosity on the vertical axis and time on the horizontal axis, and we have an event that has this typical shape, and the spectra indicates nickel occurring in the peak of the luminosity, and that nickel's decaying away, and later in time we primarily see the decay of cobalt, you may have a supernova type 1a event. On the left, we're looking at an image of G299 that may be one of these type 1a supernova events. We're looking here at the supernova remnant. The center area is generally where the supernova event began. In the event that leads up to the supernova, we have a white dwarf, which you can't see in this sketch, but it's primarily located at the center of the accretion disk. And it has reached a critical mass of 1.44 solar masses or greater by accretion. So the accretion is coming from the secondary star. The accretion slowly spirals in and lands on that white dwarf. And once the total mass of this white dwarf exceeds 1.44 solar masses, then we can have fusion occurring in the core, and it's going to be carbon fusion. Now, this fusion is not going to be stable fusion. It's going to be unstable carbon fusion, which is going to cause the entire white dwarf to explode. And when it explodes, it has this dramatic rise in luminosity. We see nickel primarily in the spectra at the peak luminosity, and that nickel's decaying away. And then later on, we see the decay of cobalt in the spectra. Typically, this scenario is a type 1a supernova.